I can't believe this. A 10x speedup with a vector? Well, that's what a fellow colleague of mine, Chris, did. He replaced an unordered map with a vector and got a 10x speedup. And that went against a very basic computer science fact, which is that for any specific operation, the big O time complexity of a vector is greater than or equal to the big O time complexity for an unordered map. This is what we learn. This is what we use on interviews. Yet reality differs a bit. Hi, my name is Michelle, and I'm a software engineer at Bloomberg, where I write code for the order management platform that traders use to buy and sell securities on the exchange. Billions of dollars flow through our system, and so yes, of course, speed matters. But I think I'm truly an undercover detective because I love knowing the how and why behind the things that work. And I'm powered by curiosity, caffeine, and Stack Overflow to do so. And any good detective knows that no case is ever cracked alone. And so if you have something to share or a question to ask, please do leave those till the end. But we are going to go on this journey together, so stay alert. My detective ducks will at least tell you that. All right, let's get back on the case. This 10x speedup by replacing an unordered map with a vector. What really happened? Well, here's a sort of simplified version. And what was really done in production is that there was some data structure with keys, and these keys were being looped through. And what we're doing here in this toy example is timing that for loop. So we look at our key, we search for it in our unordered map, and then we get the corresponding value and use it in a sum. And we do this for each of our keys. Now, the alternative here, which was the replacement, was using a vector instead. But before I go there, the big O time complexity here was O of k, because you're looping through each of those keys, and k is the number of keys. But what happened in the vector case? Well, really similar. What we're doing is we loop through the keys again, and we use the value in the key as an index into the vector, and we get the value there and use it in the sum. Once again, we do it for each of the keys, and we time that for loop. What's the big O time complexity? Well, again, it's O of k, where k is the number of keys. But even though these two things had the exact same big O time complexity, the vector was 15 times faster in this toy example. That's crazy. Well, at least I thought so. And I started gathering intel. I asked around, hey, why did this work? Do you know? Well, and most people didn't. People in this room, my fellow detectives, does anyone here know why the vector was faster than that unordered map? Raise your hand. Okay, I see someone here quickly. So, oh, perfect. Right next to the mic. Okay, so the person said cache locality. That's correct. Are you good at catching? Because I suck at throwing, but this is a detective duck for you. Perfect catch. So cache locality was one of the reasons. There are a lot of reasons. There's also hashing, which takes time, and that happens in the unordered map. There's potential collisions that can happen in the unordered map. And there's no pointer chasing in the vector, right? But of course, there's contiguous memory, so we have cache locality. Just out of curiosity, could you raise your hand if you already knew about this? Okay, so it's almost, I think, 3/4 of the room. Nice. Today we're going to cover data structures and contiguous cache memory before we pivot onto really how to utilize your cache when you write code. And we'll wrap up with the intersection of caches and threads. So we had contiguous memory for that vector. But for the unordered map, things were a little different. And I know I showed you this diagram, but the first rule of being a detective is to trust no one, including me. Because the thing is, it's a little more complicated, not too much so, but you have these keys, and then there's the hash function that gets applied on each one of them. And they essentially map to a particular bucket. And these buckets have nodes attached to them. And these nodes are actually not contiguous memory. So memory is not one after the other, like it was in the case of the vector. But why does this matter? Well, we do need to drill down to what our caches look like. And if you think about this diagram, where those tiny boxes represent 8 bytes of memory, what happens is when you try to access the very first element of your vector of doubles, where in this architecture, a double is going to be 8 bytes, what happens is, well, let's say the whole vector is in memory. And in this case, you'd have to first look in the cache, and you see, oh no, the vector isn't there. And because of that, you get a cache miss, and then you go on to main memory, and you finally find your first element of your vector. But here's the catch. You can't actually move just a single byte or a few bytes at a time from main memory to the cache. You have to move the whole cache line. And a cache line is typically 64 bytes in x86. It does vary. And in ARM, it tends to be 32. So you grab this whole cache line, and even though you care about that whole, just the first 8 bytes, you're moving the whole cache line to your cache. And that includes potentially having that second element of the vector in there, because a vector has contiguous memory. Now, what if you wanted to access that second element? Well, it's most likely already in the cache because it was most likely on the same cache line, so you have a cache hit. But for the unordered map, if you were trying to get the second element, you most likely would have a cache miss, just because unordered maps, not contiguous memory. So what if there's a cache miss? Who cares, right? I mean, doesn't matter. But it does, because if you think about the architecture of your program, or sorry, your computer or device, you tend to have essentially memory stores. And the further away you are from your control unit, the longer time it takes to actually retrieve this data. And to really visualize this, we have those lovely little bouncy balls. And the pink one is the data movement to and from a register. It is pretty quick compared to the other balls. The blue one represents data movement to and from the cache, the L2 cache specifically. The green one, which is much slower, is movement to and from primary memory. And please, let's not talk about the secondary memory ball. That's so slow, it's barely even moving. But yeah, the long story short here is cache misses are bad. So let's think about data structures. Some data structures don't actually have contiguous memory. So that's all over here. For example, std map, std set, etc. And even outside the standard library, you might have even boost having the unordered set. This is not contiguous memory. It has other benefits, such as maybe a better hashing function, etc. But it is not contiguous memory. You also have contiguous data structures, like a vector and array in the standard. And hopefully, in C++26, we will get flat map and flat set. It was supposed to come out in 23, but I don't know what happened, standard committee. Anyway, but yeah. There was also third-party libraries with their own versions of contiguous data structures, like the flat hash set, etc. Let's take a step back. Let's understand the enemy. Non-contiguous data structures like the std set. So the way this is usually implemented isn't actually dictated by the standard. You can essentially implement a std set however you like. But most people tend to just go with a self-balancing binary search tree or a red-black tree. The contiguous version of this, like it is done with Boost's flat set, is essentially just using a contiguous vector or array to keep elements in. And these elements are sorted, so you can do a binary search to find what you want in O log n time. And std set really wins when you have a lot of insertions and deletions, because it's often just O log of n to find a position and rebalance if needed. But it tends to be O of n for a flat set, because when you insert into a vector and you want to keep that sortedness, you do need to potentially move things around. The Boost flat set has so many other wins. With lookup time, it could be faster. Iteration as well, memory overhead is lower, and cache locality is excellent. Detectives, something is suspicious on this slide. Notice how there's only a flat map and flat set in the standard that hopefully comes out in 26. There's no unordered version. Is that not strange? Well, here's what's happening. For a std unordered set, the way it's implemented is very similar, but it's essentially just a vector or array, so that's contiguous memory, of lists or forward lists for the nodes. But those nodes are not contiguous, they're scattered in memory. The flat version of that is done with an array or a vector. But the issue here is what happens if there is a collision? Well, you just put the element closest to where it was supposed to go. You can't actually have pointers because you want that contiguous memory, but just put it where the closest spot to where it needs to go. But when you do that, you actually limit your API because you wouldn't have functions like bucket const reference key, which is basically meant to return the bucket that an element is in. And there's also no max bucket count, which is an upper bound on the number of buckets. So we have a limited API to access these buckets, so this data structure is actually not standard compliant, and so is not in 26. Okay, let's pivot a bit to the curious case of the heavy work search. What we're going to do here is we have a very, search-heavy algorithm, and stuff in between each search is going to clear your caches. So this is something, at least I've quite often seen in our production code bases. So I wanted to just, test this out. And I think a lot of people might have something similar. But to really test this out, I tried to understand what my computer architecture looks like. And my best friend Task Manager said that the sum of my caches is a little over 17 megabytes. But that's for my whole computer, not just my program. So to really write a function to clear my caches or pollute them, I have a super huge array of 512 megabytes. I'm an overachiever. And I then do some more heavy work meant to just pollute my cache. So this is just the math to really show you I am indeed clearing my cache. And I then call this heavy work function, and I start timing a search. So I'm trying to just find a specific element in a data structure. I repeat this for different data structures, for 100 different search targets, for different data structure sizes, and even 25 times for each of these data structure sizes. So a lot of repetitions. And this code took one day to run. So if anyone wants to reimburse me for my electricity bill, please let me know. I didn't say that here. All right, the data structures, what were they? We have the vector, std set, std unordered set, and even boost flat set, boost unordered set, and boost unordered flat set. Detectives, can you raise your hand if you think the vector was the best? One person, two people, three. Okay, three people. Great. 4, 5. Std set? No one? Yep, that makes sense. Std unordered set, anyone? Nope, no takers. There's so much of faith in the standard library. You can see it in this room. What about boost flat set? Okay, a few hands. Maybe like 11 hands, roughly. Boost unordered set? Wow, okay. Boost unordered flat set? Okay, like 5 hands. Don't know at all? Yay! Okay, like half of the group. All right, don't worry. So I'm also asking this, by the way, for larger data structures. So larger data structure sizes, so greater than 10K. I wonder if that's why the hands didn't come up. Because maybe it depends. So I have a graph here, really showing the data sizes on the x-axis. And on my y-axis, I have the average search time for each of these data structures, represented by the different lines. I hope the colors show on the slides. And boost unordered flat set is indeed the fastest for larger values of n, where n is the data size. The std unordered set, though, ends up being the fastest for the smaller data sizes. That's interesting. And that's probably because when you have just really small data, following a pointer, and it might not be a colliding set, it might not actually be too much work. And the vector, sad, didn't do so well for larger data sizes. And this is because big O actually does apply. But if you zoom in into these smaller pieces, specifically for n less than 10, the vector actually performed the best. Yes. What about without that heavy work? What happens if we didn't actually clear our cache in between runs? Well, the same pattern actually persists in terms of which data structure does better than the others. But there's something very interesting I noticed here. So the point at which std unordered set becomes worse than the boost unordered flat set is actually shifted a little further in the case of non-heavy work, and it happens a little earlier in the case of heavy work. And the reason for this is because std set is actually making use of the cache when it is warm and not cleared by heavy work. So it's actually benefiting for more data sizes than it did before. And without heavy work, just the general times it took to search through things was faster. Ideally, we profile. What I just showed you were micro benchmarks, and these are bad. But I think it's good to know them to build intuition, and sometimes the harsh reality is that you may not always have time to profile. Don't look at me like that. But yes, always profile when you can. And honestly, you should always profile. But this is just good to build intuition. OK, so we've covered data structures and contiguous memory. Time to switch over to cache-friendly data placement. All right, so we have something like this. This is a struct with a few elements in it. So we have a character, A, which takes up 1 byte in this architecture. And then we have a double B. And because the alignment of a double is 8 bytes in this architecture, it can only essentially start at every 8th byte. So it's going to automatically sort of leave a bit of space or padding. And it's 7 bytes in this case, and then we're going to start on that 8th byte. And for character C, the alignment is 1. So it just starts right after the double. Detectives, do you know how to make this data structure smaller? Assuming we need to use every single element. I see your hand here. Before you answer, Mike, I can go, or you can go. You're faster.
Put the char after the double, the first char.
Yep, great idea.
Yeah.
Oh, I forgot to tell you this is 24 bytes. But yeah, I can put the char after the double. And do you like blue? Because you might want to watch your head. Because, okay. Good catch. Nice. All right, so we just essentially switch the ordering around. And then all of a sudden, we have a smaller data structure. And this is good because in a way, you can fit more things into your cache, potentially having fewer cache misses. There is a catch here, which is fault sharing, and I'll talk about that a bit more later. So this may not always improve your performance, but it sometimes can. OK, arrays of structs and structs of arrays. So this is something I stole from data-oriented design, mainly from the game industry, and brought it into our code base. But what we're doing is we have a struct, and we have a double for age, a double for number of solved cases, and for classification level. And we have a vector of these structs. And so that's what it would look like in the cache. But what if we want to only essentially iterate through these detectives and count the number of solved cases? Well, we're actually having a few extra things in here that aren't really needed. And we can get rid of them by using a struct of arrays. Pretty simple. All we're changing here is our member variables are now vectors. And so, if we want to iterate through the number of solved cases, our cache would look like this, and we could potentially have fewer cache misses. There's also this row-wise over column-wise ordering. So if you have a 2D array where I is your first index and then j is the second thing you index to, what you can do is, so let's say that's your array, and then I increases along the x-axis, j essentially increases or decreases vertically. That's what your data structure would look like. And in your cache, it would look like this. So that's just the first two elements with I as 0. Then you have the next ones with the next I, and so on and so forth. Now, if your inner loop is indexing based on I, and it's basically incrementing I, what's going to happen is you look at your first element, that's fine, but then you skip over some of those elements in your cache, even though at some point you're going to come back to them, and you look at the next I, so I equals 1, and that's what you see. Again, you increment I by 1, you're skipping over things, which is bad, and so on and so forth. And the second you have more I, so you're incrementing I, and there's no space in your cache, you probably have to evict something to fit what you want in there. And this is bad because at some point, you have to come back to what you just evicted. So the easy fix to this is literally just swap the loops, make your inner loop increment j instead, and then you just access things in your cache one after the other. So I remember when learning about this, I had watched a conference talk, and it said that the declaration order matters. And it kind of makes sense, right? So if you declare an int x, and then you do some heavy work in between, and then you use x again, that most likely, well, it should be slower than essentially using x right after you declare it, right? How many of you agree with this? Okay, half the room. How many don't agree? One person? Wow, you're two people, cool. It wasn't a conference talk, so yeah, good point. So we trust no one. That was a very good point. Actually, you deserve a duck. Do you want? There's a cup there. It might break. It's not my fault. Catch. Poor duck. All right. So I tried testing this out myself, and I have scenario A, so this function. What it's doing is it's declaring this volatile int x. I had used volatile to not prevent a compiler optimization and essentially prevent constant folding in this case, but we'll talk about that later. I then pollute the cache, and then I start timing, essentially using x again to calculate another variable y. Simple enough. If you like colors, you can remember, I hope, okay, it's fine. Yeah, green, red, green is the order, but yeah. Scenario B is very similar. I declare my variable, but I immediately access it, and I'm timing that access. And then I do heavy work at the end. And I have main, and I run scenario A first in main, and then scenario B. Simple enough. And I got a speedup. Woo! Haha, you were wrong. Or were you? So I switched the order of A and B in that main function, and then the benchmarks reversed. All of a sudden, A started becoming faster than B. So it's literally just swapping those two things. Does anyone know why A suddenly became faster than B when B was run first? Please raise your hand. Give it a thought. Give it a thought. No one. Yeah, that was me for a good amount as well. Does it make sense to everyone? No as in no for the question. Do you have a question? Or people have understood the problem, right? Go for it. With a mic, go for it.
The reason is, even with volatile forcing it to be reloaded, when you do a whole lot of work, the actual variable gets pushed out of the cache. When you're doing the other one, the volatile is loading from the cache. So,
yeah, that's one possibility. That's a good point. Okay. You already have a duck. Do you want one more? No, okay. Start a duck farm. Anyway, so here are my thoughts. So here's the thing. The very first few instructions that you have actually run slower, potentially, than the rest of your program. Because there's something known as clock speed ramp lag. So it takes a few, 100 microseconds to a few milliseconds to actually change the internal voltages or frequencies on your device and even coordinate with any power delivery systems to essentially use more power when running your program. And your computer also needs to make sure it doesn't use too much power because then it will blow up. So all of this takes time, and the first few things will run slower. You can use tools like CPU frequency or CPU power to actually lock your CPU at max frequency. And the thing is, profiling tools like Google Benchmark do this for you automatically. I was just being a bit of an idiot and using, Stid Chrono. And I learned my lesson, I guess. Nah, not really. But yeah, so what I did was I used CPU power. I set the frequency to max frequency. And then there was still no clear winner. The evidence was inconclusive. Sometimes A was faster, sometimes B was faster. And then I realized X is an integer, right? It's super small. It can fit in a register. And so probably it was fit into that register, and then I cleared or polluted my caches, but it was still sitting in that register, right? And so it was just so easy to access it again. Another answer, yes.
Your variable is on the stack. It's right next to the return address that you had to read to come back to the function.
There was no are you talking about we are talking about return value optimization for it, or
no? Just you have a volatile variable, right? It's a stack. It's a variable on the stack. It's right next to you, whatever you just used to just do a ret from the heavy work function. Like
True.
your cache is almost always hot. Like the stack, the top of the stack is almost always hot in the cache, so that shouldn't matter.
Okay, so that's an interesting point. The top of the stack is almost always hot in the cache. I don't think I have a reason to think that was not the case in this, but that was an interesting suggestion. I'll look into that a bit more. I didn't know that. Let me throw, oh, you're so close by. Let's make it more challenging. So there we go. I almost threw this by mistake. Cool. So the thing is, I had used volatile, and I had used volatile from the perspective of making sure my compiler doesn't, at compile time, move X into where it was used. But this can actually interfere with realistic behavior. So because I had used volatile, it would actually inhibit certain optimizations, like even register usage. So X in this case wasn't even in the register. So what I just told you earlier didn't hold true. What I should have done is used things like Google benchmarks, do not optimize, because that prevents the compiler from, moving X somewhere else and messing up your timings. But it doesn't actually, stop the value from being put in the register. So I tried making X big. I made it a vector with 4 million elements. And even then, there was no clear winner. Geez. I then switched from using std.chrono to read timestamp counter, RDTSC, since the measurements were really small. It was just like tens of nanoseconds. And so std.chrono isn't necessarily the best tool for the job. And even then, there was still no clear winner. The site is self-explanatory. So, what is the first rule of being a detective? Yell it out. Trust no one, exactly. Including me, because I showed you a lovely little picture earlier, but the truth is people have, multiple cores on their CPU, hopefully, in this day and age, unless you're in embedded systems, I don't know. But normal people have multiple CPU cores. And the thing is, your program might be shifted by your operating system from one core to the other mid-run. There are also other things that run on that core, potentially messing up your timings. And so what I tried to do next was to isolate my program to only one core, making sure it's not interrupted mid-run and ensuring that nothing else runs on that core. And to do this, I first tried making sure only one program would run on this physical core. So I actually went into BIOS on my PC and turned up simultaneous multi-threading, SMT. And this prevents multiple threads from running on the same physical core. My PC became super slow after that, but we'll not talk about that here. I also tried essentially dealing with the operating system, because the OS doesn't actually, I wanted to make sure it doesn't actually run its own things on the core that I was using to test. So I used kernel boot parameters, and I did this. And I also made sure it didn't actually interrupt my task. I also used task set to just pin my program to run in a specific core. And I didn't have non-uniform memory access, NUMA, on my PC, but if you do on yours, which means you have a really high-end desktop or maybe a server, but yeah, you would do something like that instead. And even with that, it was inconsistent. Oh, the pain, the suffering. Then I started thinking, can the compiler itself move the declaration of X? Can it change what's, I hope you can see that, but can it change what's above that yellow arrow to what's below it? And it would do this only if it doesn't change the program's behavior. So it would do it for things like constant folding, but it didn't really do this for my vector. I went in and actually checked the assembly. It didn't actually move things with respect to the heavy work. And then I finally realized it's not the compiler that's the culprit. it's the CPU. During runtime, there is out-of-order execution that is being done by the CPU itself. And so what that really means is if you have a set of instructions, so I'm essentially declaring A, but it's being loaded from memory, and it is super slow, something like that can be done simultaneously with int B and int C being calculated by the CPU itself. So it's essentially doing instructions out of order. And it would only do this for instructions that are independent. And out-of-order execution will kick in, but it depends on your platform. So on my specific PC, I have Intel for my core. I did have out-of-order execution. And for things like ARM, so some CPU lines tend to not have out-of-order execution, specifically the energy-efficient cores and things for embedded microcontrollers. But most ARM CPU lines do have out-of-order execution. But it depends. OOO can kick in. But how do I test that OOO, out-of-order execution, was the culprit? Does anyone know? Hand raise. Free detective duck. Okay, I see 2 hands. You can pick who answers. Oh, so sweet. They're like, you answer. No, you answer.
You can. Okay. So you can, in a heavy order, you can pollute it with a lot of instructions, and then it won't go into instruction cache.
Yeah, that's true. You can pollute. That's one way. Let me. You have like 5 cups, 4 cups on that table. 1 mobile phone. You can catch. Nice. Well done. Did you have a different answer? Yeah. Okay.
So I think you were talking about polluting the cache. You could make the 2 sets of instructions actually related and have dependencies such that one has to happen before the other.
That's true, but it would already be in the cache then, potentially, right?
True, it would be in the cache, but at least you would avoid the out-of-order
Yeah,
execution.
that is true. Okay, you answered the question. I'll give you a duck. That's one way. I'll avoid the cups. Yeah. Oh, cool. If you want to pass that to... Thank you. Okay, 2 more hands. You can choose who answers.
Can you add a barrier?
Yeah, exactly. Hang on. I know both of you. Did you have the same answer?
Nope.
What was your answer?
Run it on different hardware?
Yeah, that's true. Exactly. You can just use a different architecture. I'll give both of 5 cups. I'm so close. I can like walk down, but destruction. Yeah. So what I did in my case was I used memory fences. And a memory fence, this is a full fence. I'm just saying that any load or store that happens before the fence will always happen before the fence. And anything that happens after will always happen after the fence. And with that, I finally had consistent results. B was finally faster than A. So variable order does matter, only if there's no out-of-order execution, and also if the variable will be evicted from where it currently is. But doing this, I think, makes your code, well, less readable than it could be. So truly only do this after you profile and you realize that this is where your bottleneck is. Okay, pivoting onto our last topic, which is the intersection of caches and threads. So we learned that I lie to you all the time, and that you can have multiple cores. Now, when you have multiple cores, you can have threads running on those cores and essentially having a copy of the same cache line. But when they care about 2 different variables, something known as fault sharing might arise. So let's say you have a thread on core 1, which cares about the value of x, and the thread on core 2 cares about the value y. But these 2 values are on the same cache line. If core 1 decides to write and change the value of x, the cache line in core 2 has to be invalidated. And if core 2 decides to read the value of y, it'll be evicted, and then the new updated cache line is brought in. So fault sharing only happens when you have multiple cores, multiple threads, and you're running so you're sharing the same cache line, and at least one core writes a variable on that shared cache line. If both of them are reading, this situation isn't going to arise. So I do have an example with something that might also be quite common in production, which is when you have counters or flags owned by different threads, and they're trying to update these counters or flags. And I have an array of these counters. So each index belongs to a different thread. And my first counter looks like this. Pretty simple. There's no padding, which means if you have an array of these counters, they most likely could be on the same cache line. I also have a padded counter, so I've used Linus. 64 is the size of my cache line, but ideally you should use something like std hardware destructive inference size. I didn't use it because it was not supported with my compiler that I was using at the time, but this is better to use. And I have an array of padded counters. And this gave me a performance improvement of 67% just by removing fault sharing. And I had only 2 threads in my example. Had I increased the threads, this would be a much higher number. And then, detectives, I tried using cache grind. And so strangely enough, the time it took was actually faster for fault sharing than in the non-fault sharing case. What? Does anyone know what happened? Please raise your hand. You can do it. I see half raised. Okay, it goes back down. I'm just talking to you. It's okay. You're good. You're good. Anyone? Hand. Yes.
It's a guess, but maybe it did not fit into the cache.
Okay, the guess was it didn't fit into the cache. That was a good guess, but it did. And the other result kind of proves it. Do you want another doc just for answering? I appreciate it. Okay. Hand, yes?
Wild guess, but is it because of overhead like on the instrumentalization by?
Good guess. And you deserve a doc. Okay, you're far. This is good. Watch your heads. If you get hurt, it's not my fault. And catch. Yay. All right, so the answer was the instrument that I used. So I used valgrind, so cache grind. And the thing is, with cache grind, is that it's actually a simulator. It doesn't actually take into account multi-core hardware effects when you have multiple threads running on different cores. So things like fault sharing with cache grind aren't actually captured. Cache grind is still an amazing tool. I use it all the time, but just be aware that some tools have limitations. So how do you fix fault sharing? Do you all want to take a guess? Anyone? Raise your hand. Hand there at the back. Okay, you can also raise your hand. There can be multiple hands raised. Yeah, behind. Did you apologize for raising your hand? Oh, you.
Well, you had a line S to fill it completely.
Yep. Do you want another dog?
I don't have one yet, so yes.
Oh, you don't? Right. Oops. That table has a lot of ducks. Yeah, you should move your head. Good to I almost hit his head. Cool. And then there was another hand. No. Oh, yes. Okay.
I did have another answer. You can use the thread local variable, and that way you don't need everything to be padded for them to have their memory locations separate.
Yeah, true. So you can use a thread local variable. Do you know if that would prevent fault sharing or completely stop it?
It depends how you use the thread local variables.
Oh, true.
But
Okay.
yes, in this case, it would prevent false sharing.
Yeah, not prohibit. Okay. Now I will throw. You got this. Okay. I'm gonna start like going into professional sports after this talk. All right. So, and before oops, no one saw that. Unsee. Any other answers? No. Okay. So one other way is also data structure reorganization. So if you have a struct and you have member variables right next to each other, you can just move them a bit further apart. If they're accessed by different threads, potentially, that will fix fault sharing. The thread local variables, so these are temporary variables owned by a thread, and they lie on the stack. And each thread has their own stack, which is great. These, though, prevent fault sharing in most cases. There's a tiny chance it won't in the case that your variable lies at the very bottom of one stack and then the top of the other stack. But this is highly unlikely because stack sizes tend to be even pages long. So yeah. There's also, did you say local variables or thread local? Wait. Thread local. Oops. Well, this is also, the same thing applies. Thread local storage is very similar to local variables on the thread, except the storage duration is longer, so you can have global or static storage. Again, this doesn't prohibit fault sharing. And there are just several tools you can use to profile the behavior of your cache. They're over here, and I won't go through them. But in summary, you, my dear detectives, have cached it. You've seen how contiguous data structures improve performance. Hopefully, you've learned to avoid fault sharing. And you've learned that cache-aware reasoning beats raw intuition. And of course, heeding the right tool in the right way is super important. Efficiency isn't just about big O. And last but not the least, data access patterns are everything. And of course, please trust other people. I know what I said earlier, but ignore that. But always verify things yourself to build understanding when possible. There are some other great related talks. I do want to give a shout out to Chandler because you are my idol. But yeah, you're one of the reasons this talk exists. So all a list of amazing talks. But yeah, that's basically it. Hope I cached your attention. Time to evict myself. Thank you. And questions? I still have a few ducks left. So if you're able to ask a question I can't answer, or even just ask a question in general, I'll give you a duck. Okay, question there? Yeah.
Thanks for the talk. A couple slides back there on thread local storage, there was just a brief little note at the end there that said, thread local storage is bad in my opinion. Yeah. Could you elaborate on that?
Yeah, the reason I said thread local storage is bad in my opinion is because it has the same negatives as like global variables do. I know Bloomberg itself uses thread local in a lot of our things, so it's not necessarily bad, but if you can use local variables instead, opt for that instead. But yeah. Let me throw you a duck. And I hope you can catch. There's a glass, be careful. Okay, good catch, nice. Question?
Did Chris Cotter, who inspired your detective work, agree with your conclusions?
Good question. So here you go. This is a duck. No, I should have thrown it to you. Okay, it's fine. So Chris Cotter is the reason also for this talk because it inspired this. He did agree with my conclusions. I ran this past him. And it was pretty interesting because he didn't actually think about the reason initially behind why this worked. He saw this in the wild as an optimization, and he tried it out on our code base, and it worked. And so that was the end of the story. But this is the part 2. And I think he hopefully also learned something from it. But yeah.
Yes, so actually in the very beginning we were talking about the flat set and everything. My question is, if
data structures that you're like trying to store in container is really huge, way bigger than any cache you can possibly have. Wouldn't it be better to have multiple flat sets or whatever rather than a single big one?
So it depends on how you're using them. That's a good suggestion. It depends how you're using them, because eventually, won't you be bringing them into memory anyway? Are you talking about SIMD stuff? Like, so you can parallelize the flat sets? Yeah, that's true. That's a very good suggestion. And you can get a duck. And the camera stuff is dead. No one cares. Oops, oops, are you okay? You even moved out of the way to like not be hit. And are you fine? Okay. Okay, yeah, you deserve a duck for that. Fine. Now, other people are going to try to get hit just because of this. Don't get hit. I won't give you a duck if you get hit. There we go. Other questions? Hand? No hand? Hand? Yes. I saw one there as well.
This is less of a question, more of a comment, but specifically on your data-oriented design thing, the section of the talk. It's not a question; it's more a comment. There was a talk I saw a while ago on it's somewhere on the internet. It's by Andrew Kelly, and he's the guy who created Zig, and he went into a lot of detail regarding that and a lot of the stuff you talked about, and it was one of the talks that like really helped shore up that stuff for me. So even though it's in Zig and not like C++, like I thought it was pretty cool, and it was a good resource for everyone.
Thank you for sharing that. That's amazing. I will check that out, and if I can add it to this list so that everyone else has it as well. It's Andrew Kelly, you said, right? And you deserve a duck. You deserve 2 ducks for that, but I will not throw the duck in the food. Heather, do you want to... Oh, no. Do you want to move out of the way? I want to throw. Catch. Cool. You can sit back down. Any other questions? I saw a last hand there, and... Okay, cool.
I've been experimenting lately with using WebAssembly, and because that's a bit abstracted from the hardware, I wonder if you've tried any of that, or if you have suggestions for whether I'm not even sure how to use some of the performance measuring tools there. So I'm just curious if you had any experience or thoughts on that.
Good question. I've not used WebAssembly so far, but I might use that for my next detective deep dive. But if you're not able to access your hardware, I had this situation in production. Things like cache grind, because it's a simulator, work really well. That's why it exists, like in a way. But yeah, there are probably other tools out there as well that help with these things, but that's one suggestion. Anyone else have any other suggestions for the WebAssembly question? Oh, no. Okay, so no hope for you. No, I'm pretty sure. We can look into that later. But you deserve a duck. And the lights are going to get hit, and I don't care. And nope. Cool. Okay, any last questions? This will be the last one, if any, I think. Yep.
So you mentioned that padding and alignment is one way to deal with cache problems, right? So this might be a stupid question, but if the cache lines are different in like different architectures, how do you deal with that in your code?
Good question. So are you talking about also not a stupid question, don't worry. Are you talking about like the size of the cache line?
Yes. Yeah, I think you mentioned earlier in your presentation that there are some like different cache line sizes.
Yeah, that's true. So that's why things like STID destructive hardware inference size, that thing, is useful. You should not be hard coding cache line sizes like I did. So that's the way around that. But yeah.
Okay, thank you.
Yeah, and you deserve a duck. So yes, move out of the way. Yes, move. And cool. Great. That's basically it, I think, time-wise. Yeah. Thank you so much. And if you want a duck, please come up and grab one.